learn like a pro.
We're surrounded by sound every single second, but we almost never think about what it really is. What if sound wasn't just something you hear, but something you could actually build with? Today, we're going to look at the architecture of sound, the physical rules that let us engineer it into amazing tools, from a simple echo to a complex map of the ocean floor. So that's our big question, our design challenge for today. How do we take this invisible wave and turn it into a precision instrument, one that can see through solid objects or chart out the deep sea? Well, it all starts with understanding the basic code of the wave itself. All right, let's get right into the mechanics. If you want to build with sound, you have to master its two most fundamental properties. Seriously, everything from a tiny whisper to a powerful sonar ping is just a mix of these two variables. So on the left, you've got pitch. That's all about frequency. Basically, how many waves are packed into each second. The more waves, the higher the pitch. Simple. On the right, we've got loudness. This is all about amplitude, the height of the wave. A taller wave carries more energy, and that means a louder sound. It's a really direct mechanical relationship. And this chart here lays out all the possibilities perfectly. Take a look at the top right. High amplitude and high frequency. That gives you a loud, high-pitched sound. Now, look at the bottom left. Low amplitude and low frequency, and you get a soft, low-pitched sound. By just tweaking these two things, we can basically create any sound we want. But here's the catch, a really crucial design limit, our own ears. The typical human ear can only hear frequencies between about 20 and 20,000 hertz. Anything below or above that range, it's completely silent to us. But, and this is the important part, just because we can't hear it doesn't mean we can't use it. Okay, so we've got the properties of the wave down. Now let's see what happens when we send that wave out into the world. How does it interact with stuff? Well, this is where the whole idea of an echo comes into play. You see, an echo isn't some random thing. It's pure physics. Sound bounces off surfaces with incredible precision, kind of like a pool ball hitting the side of the table. The angle it hits the surface, that's the angle of incidence, is always, and I mean always, identical to the angle it bounces off. This simple, reliable rule is the key to everything else we're going to talk about. So that leads to a pretty logical question, right? If it's a perfect reflection, why does an echo always sound weaker or softer than the original sound? Well, the answer is all about energy loss. A sound wave isn't just traveling through empty space. It's physically pushing against air molecules. And with every single push, it loses a tiny bit of its energy to its surroundings. So by the time that wave travels to a wall, bounces back, and travels all the way back to your ears, its amplitude, its energy, has dropped. And that's why the echo is always quieter. Okay, so let's put it all together. We have a wave that reflects predictably and comes back with a little less energy. With just that knowledge, we can now create a blueprint for measurement. We can turn that simple echo into a seriously precise calculation tool. The whole process is actually elegant and simple. Step 1. A device, an emitter, sends out a controlled pulse of sound. Step 2, that pulse travels through the air, hits a target, and bounces back. And step 3, a receiver detects that returning echo, very carefully measuring the time it took for the whole round trip. And all of that boils down to one single essential formula. The distance to an object is simply the speed of sound multiplied by the time it took. But, and this is the part you absolutely can't forget, you have to divide that number by 2. Why? Because the time you measured was for the sound to travel there and back. We only care about the one-way distance, so we cut it in half. All right, let's put this formula to work. In our first blueprint, we're in a place where we already know the distances. So by sending out a sound and timing the delay between the echoes, we can actually work backwards to solve for the one thing we don't know, the speed of sound itself. And in this example, it works out to 325 meters per second. Now let's flip the problem around. In this blueprint, we already know the speed of sound. Imagine you're in a canyon, you clap, and you hear the first echo after 2 seconds, and the second one after 3 seconds. Using our formula, we can calculate the distance to each cliff, and then just add them together. And just like that, we've accurately mapped the width of the canyon, 825 meters, using nothing but a sound and a stopwatch. So far, pretty much everything we've talked about has been sound that we can actually hear. But the most powerful, really game-changing applications of this stuff happen at frequencies way beyond what our ears can handle. This is the world of ultrasound. So, what is ultrasound? The definition is totally straightforward. It's just any sound wave with a frequency higher than 20,000 hertz, which is that absolute ceiling of human hearing. Our entire audible world is just this tiny little sliver of the full acoustic spectrum. Beyond that 20,000 hertz line lies this vast, silent range of ultrasound. It's a spectrum we figured out how to engineer for super high precision work, letting us see things our eyes never could.
And the applications for this tech are just incredible. In manufacturing, we can shoot ultrasound pulses into metal to detect tiny microscopic cracks, preventing catastrophic failures. In medicine, those same waves reflect off different layers of tissue to give us the very first images of an unborn child. And out in the ocean, they map the seafloor and find schools of fish, revealing a world that's usually hidden in total darkness.
And this is where it all comes together. Sonar. It's the perfect synthesis of every single principle we've covered. You've got a high-frequency, high-amplitude ultrasound pulse that gets fired off. It travels down, reflects perfectly off the ocean floor, according to the law of reflection, and the returning echo gets timed by a sensor. Then a computer just runs that simple formula. Distance equals speed times time divided by 2. And boom, you have the exact depth. Every concept working together in perfect harmony. So we started with a simple wave, and we ended with a tool that can see through steel and map the deepest parts of the ocean. It really makes you wonder, doesn't it? What other invisible forces are all around us, just waiting for us to decode their architecture and start building with them?